This was, did I plug in mine? Would it unsettle if I plug in this?
You can take it, yeah, directed it.
Okay, this is,
Yes, we are trying to, it's helping me what
okay,
yeah, yes. And it's not able to stand here and it's
There's always a smart stuff. It's not so flimsy.
it's good for me to move around. Standing at some. I'll probably try.
Just transition.
He's having the given.
But you can.
Okay, yeah. Right.
Yeah.
College.
This is good. I bought this just 3 days ago. I didn't use this.
Okay.
Okay, yeah, but
Yeah,
So-
Rex.
exactly this button is important. There's two buttons,
Okay.
up and down. Don't use something else.
Okay.
Okay.
Thank you. You want a short speech before we start? Okay, so I can see.
Good morning, everyone. Did you have a good night's sleep? For those of you who are visitors, we're really happy that the weather's still holding up and us putting on its best performance. And it's my great privilege today to host 4 incredible international speakers here at AIMS, who are going to give 4 public lectures during the course of the day. AIMS, as you all know, is 20 years old this year, and in celebration, we are also interviewing for a German research chair at AIMS. All 4 public lectures are part of the interview process for the next German research chair here at the African Institute. I just want to go through the order of proceedings for the day. We've got 4 lectures. We start in about 10 minutes with Dr. Ines Mundler, who's going to speak to us about overdetermined boundary value problems. And then you'll notice that there's a 15-minute break between each of the public talks. It is because I find that if I engage with really mathematically challenging topics, I sometimes just need to stand up and stretch my legs a bit and get the blood flowing again instead of sitting for 2 hours on constant lecture. So that gives you time to run outside, see the beach, go to the bathroom, grab a cup of coffee, and come back again to the next door. You're welcome at any point in anyone's talk to raise your hand and ask questions. Also, at the end of the talk, really please engage with everyone who's speaking to us today. Then Professor Sergei Rozhanov is speaking about the world of particles, and then we'll finish with a Heritage Day lunch. That will be the first part of the morning. So a couple of days ago in South Africa, we had a national festival, a national holiday, that's called Heritage Day, where we celebrate our national heritage. So it's a chance for all of us to rip out our favorite costumes. I grew up next to SOT or Swaziland, so this is what I'm wearing today. So we'll have a barbecue or braai outside, just to celebrate Heritage Day. Everyone's welcome to join for that. Then we'll have 2 more lectures after public talks after lunch. Dr. Bruce Bartlett is speaking about quantum topology and topological quantum computing. And then that's followed by another quantum lecture by Dr. Ryan Sweeker, speaking about quantum machine learning and an overview of its potential and limitations. And then we'll conclude the day with a talk by the Google Foundation to tell us about their work, what they do, and what the global network is all about. So without further ado, I'd like to introduce Dr. Ines Mundler, who's an assistant professor at the University of Douala in Cameroon. And I'm going to steal your thunder a little bit, if that's okay. He's a world-leading researcher. He studies partial differential equations and the global analysis of manifolds. So I'm a machine learning researcher, so all of these things would be wonderful and new to me. I'm looking forward to it. He also researches the connection between many domains. The construction of problems, which are solvable, Giga sets, which I don't know what they are, so I'm looking forward to this. And Mean curvature surfaces is interested in non-local analysis of non-local operators, and the study of hypersurfaces, constant local mean curvatures. I feel like this should sit here with the whole notebook. Yeah. We had a number of other research interests, including partial differential equations, the analysis of free boundary problems, non-local analysis, and minimization of hardy solid motions. And furthermore, is interested in the global analysis of manifolds, overdetermined problems, manifolds, and so on. He has a PhD from the University of Cheikh Anta Diop in Senegal. And so everyone, please welcome Dr. Millet for the first public lecture.
So thank you very much for the nice introduction. I connect the slide. So I would also like to thank the organizer of this important scientific event for providing this facility as my first time to South Africa, and I'm enjoy the campus hospitality. Today, I am talking about overspan boundary value program. This is a research direction of the project submitted for this position with my cooperation partner, Professor Dr. Tobias Beck. And the type of overspan boundary value program we are dealing with from this talk are of two classes. The first class is of Dirichlet type, and this first class has been intensively studied in the literature. The second class remains less studied. The reason being that solving an overspan boundary value program of Neumann type comes with a mineral loss of derivatives, and the loss of derivative is a challenging problem and the study of partial differential equation. Such a loss is not present when solving over the determined boundary value program of Dirichlet type. And an important question is to know how one can overcome such a loss of regularity. A common tool is I don't know how this. Let me try this. Yes, I was meaning a common tool in dealing with the loss of derivative is the use of Nash-Moser iteration techniques, but these techniques is difficult to apply. In fact, if you want to use bifurcation theory, there is no abstract bifurcation theorem in the Nash-Moser framework, at least to our level of information. And even in case of possibility, it is difficult to satisfy the tameness assumption within the iteration. So recently, we have discovered a different approach which does not involve iteration. And this approach suggests to leave the framework of standard order spaces and work in new tailor-made spaces to overcome the loss of derivative. And this approach is the main target of my talk, and I will be happy to know that most of you have learned how it works. I will explain this approach in the third part of my presentation, dealing with the Schiffer problem on the cylinder and on the tooth here, after introducing the study of overdetermined boundary value problem in part 1. In part 2, I will present some known result on Dirichlet boundary value problems. At the end, I will present some perspectives and open questions. So let me start with the introduction. Overdetermined boundary value problem appears in fluid dynamics, and here is a model where we have a fluid and a long pipe of cross section omega in the plane, and the aim of this model is to determine the cross section and the flow velocity u. But under some consideration, the flow velocity u satisfies this Poisson equation where the condition u equal to 0 is the so-called adherence condition. If omega is a smooth bond, that one can then prove existence and uniqueness of solution to this problem. But at this stage, we do not know the shape of the cross section omega. Further, if we request the tangential stress to be constant on the whole of the pipe, meaning the flow velocity solving problem 2 has constant normal derivative we call lambda on the boundary, then we get information on the shape of our domain. In fact, after integrating by part, you see that the ratio perimeter of a volume of omega is the inverse of lambda. Problem 2, 3 is the Seren overdetermined problem. Seren was the first to address this problem in 1971 and proved that poles are the only C2 regular domain in Rn admitting a solution to this problem. Has an application in fluid dynamics. The tangential stress remains constant on the whole of the pipe along the flow if and only if the cross section omega is circular. And Seren used the moving plane method to prove this result. This is just a particular example of overdetermined boundary value problem. But in general, an overdetermined boundary value problem is a problem of form P. Delta is the Laplacian, F is a given function, A and B are real numbers, and eta is the unit outer normal of the boundary. In the case A is 0 and B does not vanish, we have a Dirichlet problem, and the Neumann problem in the case B vanishes and A is not 0. So further application of such problem appear in the linear theory of torsion, in electrostatic, in elasticity, and also in shape optimization of domain-dependent functional such as the Dirichlet and the Neumann-Hagen values. Well, I now present some recent results in the Dirichlet overdetermined boundary value problems. I start again with Seren, who considered the general case. Remember, the previous problem was set with f equal to 1. Here, f is a C1 function on R plus. Seren succeeds to prove using the moving plane method that poles are again the only smooth domain admitting positive solution to this problem. But these results classifies bounded domain admitting a solution to this problem. And the next question after Seren result was released was to know whether one can obtain a similar classification in the case of unbounded domain. In 1997, Richtig, Caffarelli, and Nirenberg conjectured if this problem admits a positive solution for a Lipschitz function, and then omega is either a ball, a half plane, a generalized cylinder, or the complement of one of this domain. It turns out that the conjecture is false. In fact, Alberto Sigbadi was the first to disprove it in 2010 by constructing a bifurcation of straight cylinder, and these domains obtained are not listed in the conjecture, which disproves it. The proof was given considering f of u equal to lambda 1 u, where lambda 1 is the first
eigenvalue of the Laplacian. In 2017, we consider the original problem of Seren with F equal to 1, and we disprove the conjecture obtaining bifurcation of thread generalized cylinders or slab, and hence including the set that were already constructed by Sibaldi and Schlenk. And an important case in the study of the Dirichlet-Overton problem is the one when F is identically 0. The corresponding domain are the so-called exceptional domain. And Trizet in 2014 was the first to classify in the lower dimension exceptional domain. We only have 3 of them, half planes, exterior of disk, and this non-trivial set omega naught that was discovered by Packard and co-authors. Well, these results is the classification of exceptional domain in dimension 2, but the classification in high dimension remained an open problem. Recently, working with Fall and Vert, and working with Vert and Wu, so these are 2 different work, we proved the existence of non-trivial exceptional subdomain in Rn, high dimension, and they are perturbation of complement of thread cylinders and the associated Rufu function, the solution to the math problem, are in this dimension bounded. They enjoy a logarithmic groove in the distance from the cylinder axis in dimension n equal to 3. The picture of this exceptional domain is given by the complement of perturbation of infinite cylinder. In fact, the domain are not the cylinder, but the exterior, since we are dealing with unbounded domain. Well, this ends the second part of my presentation, and I will just provide a list of further references where different equations have been addressed regarding overdetermined boundary value problem of Dirichlet type. I now start the third part of my presentation devoted to the Schiffer problem. The Schiffer problem is a problem of Lehmann type. It involves a loss of regularity, and as I mentioned, the loss of regularity is a challenging problem in the study of partial differential equations, and a common approach that was known before this paper was the Nash-Moser iteration, and this iteration is very hard in application. We discovered, to me, a nice idea which I would like to share with the audience. Well, what is the problem? The Schiffer problem is a long-standing open problem in the book of Yao, and the Schiffer conjectures balls are the only smooth bounded subdomain in Rn for which there exists a positive parameter and a non-trivial solution to this Neumann eigenvalue problem overdetermined by constant 1 as the boundary. This and you agree, John. You give it all. Yes, agree. Thank you. So this problem finds a connection with the Pompidou problem, which appears in tomography. And Pompidou asks to determine the class of domain for which the integral over sigma omega for sigma rigid motion vanishes. And I mean, the question here is to know whether the function f identically equal to 0 is the only continuous function on Rn for which the integral over the sigma omega, where sigma are the rigid motion on Rn. And the Pompeiu problem consists in finding all domain satisfying the Pompeiu property. Well, the link between this problem was given by Williams, who proved that a smooth and bounded domain with connected boundary fails to satisfy the Pompeiu property if and only if the over-determined boundary value problem in the Schiffer conjecture admits a positive solution. Yeah.
Could I ask if you could give some intuition why the conjectures that ground balls are the only smooth bounded subdomains? If I'm not an expert in the field, what makes ground balls?
The intuition, okay, yeah.
Unique structure.
Yeah, very nice.
Yeah, you would actually conjecture that and not.
Yeah, very nice question. In fact, round balls admits infinitely many solutions. So this is how the story starts. This problem admits infinitely many solutions on balls. And the question is to know whether the existence of a single solution on balls on a domain implies that the domain is a ball. This is where the problem starts, yeah.
You mean whether the answer is constant curvature?
The agent does not use this Alexandrov to complete that with half-balls. Because if you have constant curvatures, you have slip and you have balls. That's your question. Okay. So the intuition start with this. This problem admits infinitely many solutions on balls. And then the next question is if we have a single solution on a domain, does that imply that the domain is a ball? And some positive results are given by Berenstein, Bach, Aviles in low dimension. So this is where the question starts. So, some positive results are available in low dimension, but in general, the conjecture is still open, even the Pompeiu problem in Rn. So this problem is open in Rn, but one would like to know whether there are some positive results in the general Riemannian manifold. Schlover was the first to study this problem. And under this setting, we say that the bounded domain in a complete Riemannian manifold is the Schiffer domain, provided this over-determined problem admits the solution. Delta G here is the Laplace Beltrami operator with respect to the metric G. Schlover proved the existence of Schiffer domain having constant principal curvature on the sphere Sn. And the question that was left after this result was to know whether in a general Riemannian manifold, the border of every Schiffer domain has a constant principal curvature. And our first result addresses this question, and the answer is no. We disprove it on the manifold given by the flat cylinder. Our second question here is a conjecture by Swan, who studied the case n equal to d that was not covered by Schlover. He proved if omega is a C2 alpha domain admitting a solution to the Neumann eigenvalue problem of Riemann by 1, and either one of these condition hold mu is 2 and omega is simply connected, or mu is the second eigenvalue of the Dirichlet Laplacian, then omega is a geodesic disk. In the same paper, a conjecture, a Schiffer domain on S2 must either be a ball, a geodesic disk, or an axially symmetric annulus. In our second main result, which is proof this conjecture. Well, I now go step by step, presenting our main result on the flat cylinder. We are using bifurcation theory, and you have to bifurcate from a trivial branch. So we have to get a trivial branch. The trivial branch here is given by the Nernst-Neumann eigenfunction of the Laplacian on the unit ball. We extend it on the whole space and obtain a trivial solution, a trivial branch of solution on the fixed domain omega star. And then we need to bifurcate omega star by constructing domains of the form omega h, where h is a positive function of class alpha, periodic and even. Under this setting, we use bifurcation theory and prove for n and m positive integers. We have a curve with two components, and the boundary parameter h we are seeking for here to construct omega h has this expansion has s tends to 0 uniformly on R, and on omega hs, this problem admits a solution which is radial in the t variable and 2π periodic and even in x. We also know the expansion of the solution as s tends to 0 in terms of the nth Neumann-Hagen function, and phi1 is a positive first Dirichlet Hagen function of the Laplacian on the ball, given as in terms of the Bessel function of the Bessel function G. The constant and the theorem are explicit in this remark. We also state our second main result on the two sphere. Again, we take a periodic function larger than 2/π, and we define the second by phi. The Laplacian has this representation in coordinate tx. Here we have the trivial branch given by a symmetric neighborhood of the equator. When h is not constant, we have bifurcation of this neighborhood. The trivial branch of solution is here given by the first positive Neumann Hagen function of this problem. With this, we approved for large L the existence of a curve with t component. H of s has this representation. It is the boundary parameter we need to construct. And on this domain omega hs, this will determine boundary value problem admits a classical solution. I now sketch the proof only for the case of the flat cylinder because of time constraint. Well, a general approach is to reformulate the overdetermined problem as a parameter-dependent nonlinear operator equation f lambda UH with the condition that we have a trivial branch. Then H here, as I said, is plays the role of the boundary parameter, and U is the unknown in the Dirichlet in the overdetermined problem. After this reformulation, we can apply bifurcation theory, namely the Crandall-Rabinovich theorem or topological fixed point theory. Here, there are two ways to solving this. If the trivial branch enjoys non-degeneracy property, then you first solve problem the equation 7 by expressing u in terms of the parameter lambda and h, implicit function theorem, and you end up expressing h in terms of lambda. If not, you have to express the unknown h to the converse in terms of u by finding the solution form via the trivial branch of solution. In our case, we have no such non-degenerate property, so we will use the second strategy. Let me recall our problem. We are interested in solving problem n in the domain omega h, where omega star is the fixed domain. We need a lambda dependent equation. For that, we introduce the operator L lambda here, and we observe that a function u solves this problem where the operator L lambda is involved if and only if W lambda solves our original problem in the domain omega h over square root of lambda. So we are then interested, since we need a lambda parameter, lambda dependent problem, we are interested in solving problem m. We pull back this problem on the fixed domain and obtain problem 9. The operator LH lambda here is the pullback operator of L lambda that we obtain from this compatibility relation, and L lambda H is known here. Well, we need to reformulate this problem into an equation of form f lambda u h equal to 0. And we do it here by defining f, and this way, here f lambda u h is L1 plus h lambda applied to un plus n plus u. Un is the trivial branch of solution. Compare this equation with the definition of f lambda. We observe by constriction that if you solve this equation, then you have just produced a solution u tilde given by un plus u to problem 12, where h is now replaced by 1 plus h. Now, we try to solve this problem under this setting, but we fail because we meet a loss of derivative. So I am first explaining how this setting leads to a loss of derivative of order 1. I mean, dealing with this equation, you want to know the regularity of V and H. But under this change of variable, you obtain this PDE, and regularity theory tells you that if F is in C0 alpha, U is in C2 alpha, but then H, which involves the derivative of U, is in C1 alpha, V is also in C1 alpha. You are losing derivative of order 1, so you fail. You need to change the strategy. I am now going to explain our trick and the intuition behind overcoming the loss of derivative. Keep in mind that you need to produce the solution form from the trivial branch. The solution form itself just drives you to the right functional setting. And this argument has already been adopted by some experts in this field who are dealing with a different type of Schiffer problem. The steps in constructing the right functional setting are the following. You use the trivial branch which solves this equation. Then the compatibility between the pullback operator and the operator L lambda tells you that the solution to the interior equation is given by UHN. Then you expand UHN to see that your solution form is the sum of three functions, the first, the second, and the third that you don't know, this zero term, call it U. But then, since you want this function U tilde to satisfy the required assumption, U tilde must be 1, you end up seeing that U must be 0 on the boundary. This is one condition on the space you have to define. The second condition is you want this derivative to vanish on the boundary, but it tells you that Hx is then known in terms of this derivative, but since you need H to be C2 alpha, this derivative has to be C2 alpha. So the solution form is telling you where you have to go. Then the word functional setting is to consider the space of function vanishing on the boundary and having a C2 here. I'm writing everything in the K index. Now you define this space XTN with this condition that was not considered in the previous space C2 alpha GN, where the loss of derivative occurred. And we are going to see that under this setting, we get regularity. In fact, the operator F lambda here is well defined. It targets Y, not C0 alpha. In fact, C0 alpha was big enough to gain regularity. This is the problem. Well, now we again regularity by revising this equation again. We see that U is in X2D, but the definition of X2D is that this derivative of C2 alpha, H is a constant times this derivative is C2 alpha. And then using the fact that capital U is C2 alpha, H is C2 alpha, V is C2 alpha, you recover the loss of derivative. In fact, the claim is just a consequence of this regularity result that we prove by writing the interior equation satisfied by DTU. The right-hand side here is in C0 alpha, the boundary equation of DTU, this is U. The right-hand side is in C alpha, C1 alpha, meaning that DT is in C2 alpha, and the loss of derivative is recovered. So this ends the second part of my talk, and my aim was to explain how we lose regularity and how we recover it. Solving the problem follows step by step the general strategy I presented at the beginning of the proof. I end this talk by explaining that after writing this paper, our argument just opened a bunch of perspectives that I can discuss with you over the question session. I have chosen 4 of them, and we are left, nevertheless, with 2 open questions, and we don't know how to solve them. We do not know how to reformulate the Nash-Moser relation to ease it using our argument, and we do not also know how to improve the Grandal-Rabinovich bifurcation theorem in the presence of loss of derivative. In fact, we tried it. You have to satisfy like 10 assumptions, and this abstract version was not quite nice for us. And this work is unpublished. So I end my presentation here. Thank you very much.
Thank you very much, Dr. Moonen. I now open the floor for questions and discussion. So what is you? Yes. Yes. And we can just repeat it at the front.
Okay, you were saying that this overshirt is normal, actually, boundary value proposed by niche or applications in electrostatics.
Yeah, they are correct, you know.
Considering your main results, can you give us a particular example of this area where there could be important application problems where your results could be?
Yeah, and we got a result in the Dirichlet boundary value program that made explain how I will present the I'm coming, please, just to be on the same level. Yeah, this one. This one. This program. So in R3, this problem appears in electrostatics, and that you here
You say what it is in electrostatics.
I'm explaining. U here is the single layer potential explaining induced by the constant charge density 1 on the surface. And an important question here for this problem is to classify surfaces admitting constant charge density 1 in the absence of exterior field. Such charge density are called equilibrium charge density, and this problem was addressed by Rachel. Rachel proved that Porsche are the only C2 alpha domain whose bond admit constant charge density in the absence of exterior field. And in dimension 3, we were motivated by this electrostatic formulation of the problem to produce hypersurfaces on bounded 1 where this type of property also holds. Property that the constant charge density 1 is an electrostatic equilibrium. This is just the explanation. What is the meaning of that in mathematics? So, you define the normal component of the electric field property that the constant charge distribution is an electrostatic equilibrium is that Nx plus 1/2 vanishes at the boundary. And what is the link with this Overschumann boundary value problem? There is a jump condition satisfied by this electrostatic potential that the normal derivative is x plus 1/2 on the boundary. So if you solve this electrostatic equation, which means that the constant charge density Y is an electrostatic equilibrium, you are producing a solution U with vanishing derivative. And then from this solution, you are able to construct another solution with non-constant. So this electrostatic formulation leads one to the construction of exceptional subdomain in dimension 3. What we use. So we didn't solve directly these problems in dimension 3 because the electrostatic characterization goes from that. In dimension 4, such a characterization is not possible. And in fact, the difference between these two problems is that the form of the fundamental solution of the Laplacian, which is logarithmic in lower dimension, and is a modulus over 2 minus n in higher dimension. So this was the difference between this and that 1.4 and 1.
Let me repeat the question. We gave our mathematical explanation, but where in the real world does this appear and where could you use it? That is for application. About application outside.
Okay.
Electrostatics is not mathematics.
Yeah. Okay. Yeah.
Batteries or
Electrostatics application will certainly appear to theory. But I should mention that most of these problems appear in modeling disease. There are 3 more problems. They appear in modeling population dynamics. There are 3 more problems. How the population evolves, that means how the space where people live evolves in time. Because we are not only interested in this in the solution U, we are also interested in the boundary behavior of the domain where some dynamics is happening. They also appear in modeling cancer. Cancer evolves.
what does it explain in modeling cancer? What do your results explain when you model cancer?
Okay, the evolution of cancers. Determining U means determine the density of cancer. Determining the boundary of the domain in few boundary problem tells you how fast the cancer grows. And from this information, you can provide recommendation to examples.
Your domains are very special. Assuming domains all the time of a certain shape, cancer doesn't need such a regular structure. Thanks. No, the oligos are very special.
Yeah. For the exception. Yeah, for the exception and factor. Yes, yes. Yes, they are a lot. Yeah, I understand. Cancer is in the body domain, cannot go to the body. This case. But this problem are not only solved in the field on board domain, you can also solve them in other domains which are not certainly false, because false appear in the rigidity soil.
Are there computational methods that actually do that?
Computational,
Yeah, no, you have a theory and explain something, and somebody makes X-ray information of cancer, and you predict then the growth of the tumor and the boundary of that using your theory.
yeah, I would be interested to collaborate, especially this domain that I haven't yet got to report. I have been working in the fundamental analysis of such a group. I'm excited. The guys.
I want to ask a question on behalf of our students here, and then I'll let the students also ask you guys questions. If I want to follow in your footsteps as a student, what four mathematical tools would I need to study? And then my second question related to this, which our academic director would ask you, is if I were to do a master's project or research project in this area, and face with a conjecture where we're not sure whether you can actually prove it, and I have 2 months or 6 months to produce some meaningful results that I could submit, what advice would you have as a mentor in this field to everyone who wants to follow on your footsteps, but also don't have the luxury of time to produce tangible results?
I would start with
What happens if the conjecture is wrong and you run out of 6 months? How would our students be guided through this meaty process?
for the last question workshop. It is a big risk to submit such projects to a master's student. And the second thing is disproving the conjecture is not a bad news, because it helps to inform that the conjecture is false. It will be important because then you produce the famous from conjecture set by also the famous application. Your first question was
my first
I
question
know,
was
okay,
if someone wants to follow in your footsteps, what tools do they need in the mathematical toolbox?
partial differential equations are the basics of these research. First, we need to understand both. I think it's where we start, and partial differential equations. There's this, and then we can train you some advanced courses. Thanks. Step by step.
Okay, yes. If you stand up and maybe just introduce yourself, tell where you're from.
I'm Jeremy, one of the students. I want students to explain as what's you have spoken about the proposed nice. I'll make you to maybe what's the difference between the banana and that proposed?
The other one, when we talk about topological and bification theory, we have two ways of dealing with this problem. One first case, if you are able to prove that the underlying operator F to H has a kernel, the linear operator has a kernel of one. There are extra assumptions fulfilled, then use the so-called standard bification theory. If not, you use the so-called crossing normal. There is the definition of cross normal and subparameter, and the cross normal has four. This is the topological aspect of this approach. The Kandara Mishpa cross or cross normal.
Yes, you have also, there are many sort of derivatives in some focus. In this case, you have what sort of flexibility that you have?
The differential one. We need the differential one. The Kandara.
Thanks for coming back to this question. All of this training in order to explain all the differences.
This versus one cause. That the order space is order space left. The new space is just use and the order size. One cause.
Application so clear on me, like what is the solution of these situations? And for example, from quantum mechanics, we have a Schrodinger equation. Solution of Schrodinger equation, we can get the unity of the system, and then it's economic from algorithms such as mechanical insulation and semiconductor. So I want to know the solution of this equation. What would be before this my first question. The second question, you mentioned something about charge distribution within the surface. So I want to know, did you also note the symmetry or asymmetry of the charge distribution?
Done such just guys surfaces. For the first question, what I can tell is that the solution U, here they are potential used by charge density, and the others, I have no real answer on how people use it. This is I believe will produce and people finance.
So we have two questions. Just go question 1, question 2, question 3, question 4. Okay, maybe that's all. 1, 2, 3, 4.
Predicting the algorithm. Not like the pairs. So I prepared questions.
Maybe we can repeat the questions from the front, so that the whole audience. Well, yes.
No. So, better to go.
The interior operations satisfies our which policy? Yes, it's interior, yes, we are looking at the distribution access and from this group, then there are C alpha nodes. Yes, yeah.
You go there.
We have operations at front there.
Yes. Okay, thank you very much. My name is Ben Kyung Kim. I come from the my question. The first one is to know what's kind of ship, for example, we can have this kind of application. For example, if we are in dimension 2, can we have an idea of the shape of the solution of this kind of applications? And the domains, the shape of the solution.
The solution form,
For
the expression of
yeah. The shape.
yeah, you can only expand the solution when you use bifurcation. It depends on the element of the kernel that appears. So in our case, we mostly work with even function that you can see work with all function. So in most of the cases, the kernel is generated by the cosine function. So you just start bifurcation from cosine in the plane because you use the t variable and the x variable, one of them.
If the equation is hard to solve, for example, what kind of computational method can we use to solve this?
I solve
Difference, finite difference, element, finite, or volume finite.
I have never been solving using any other method. I use on my time method solving hard solving comes of problems. Higher dimension. Yeah.
If we could just repeat the question.
Yeah. He's asking what
Is mentioned in the
high dimension.
What is high dimension? Kind of application. What's this equation?
Yeah, the exceptional domain were classified in 2 dimensions. So most when we talk about lower dimension, people talk about 1 dimension and 2 dimension. High dimension start 3, 4, and so on. So in dimension 3, we were able to produce non-trivial exceptional subdomain
meaning that the classification, even in dimension 3, is difficult. Because people always expect to produce a classification with standard domain, balls, half space, and all that we build domains that are not of this form. And we move to the next dimension, n equal to 4, where we were able to prove that in all dimensions without that or equal to 4, we have exception domain. This is the meaning of high dimension, starting from 3.
And we have 2 last questions before we wrap up the discussion. I have 1 question, but Professor David Holgate, 3 last questions. Okay, 3 last questions. So 1, 2, and 3. So Professor David Holgate says, as a topologist, I'm just reading here. I'm not going to not make eye contact. So he says, as a topologist, I'm always pleased when I see that people need or use topology in their mathematics. What would you advise a student who thinks studying topology is too abstract?
Okay. Every field in mathematics, even abstract or applied, to the brain. This is what is important, critical thinking. It's the word mathematics. So I cannot exclude any fields mathematics will allow us to study everything that can help the brain out of the box. African needs can contribute to society. In your contribution, arguing everywhere. So I would advise what to do.
And then 1 question from the front, and then the last one.
You mentioned relation Bayes' problem. Can you explain what are the implications of your results to Bayes' problem, and what are the implications in tomorrow then of your results to Bayes'?
Okay. First, if a domain fails to satisfy the objective, then it admits a solution to the Riemann problem. This is empowering.
But what do your results that apply to the status of?
Yes, in the setting of manifold, we have constructed domains admitting solution to Riemann problem in the manifold. So under this setting, we have produced domains failing the problem in the setting of Riemann, which was not the original setting.
So you disprove the generalization of these.
In fact, we disprove the generalization of the Schiffer conjecture and the manifold. This is the summary of these 2 results. The generalization.
But what's the status of the original problem? What is the status of the original problem? The problem of Bayes. Status of
The statement of
the status.
I don't know.
What is the status? What is known about?
Okay. No. Okay. It is easy to build domains satisfying the Pompeian progress. Yeah, and many of examples exist in this case. And I didn't present the first perspective. One of our perspectives is to construct domain failing the Pompeian progress.
because we know that if argument failing of good property, then you have solved the operative demand problem in the Shiba construction. And we proceed so because we believe this kind of argument can strengthen our idea in proving or disproving the Shiba conjunction. This problem appears in one of our expenses.
I have one concluding question, and then we'll take a break. As a mathematician of many tools, if you were to retire one day, I don't know if mathematicians ever retire, but if you were to retire and to look back at your career, what did the one thing be that would make you really happy? Okay. And if you can think of one thing that you look back on.
Of course, I am half happy now. I am not yet fully happy. Because I need to be happy by getting the opportunity to train the future generation, train a master's student, train PhD student, because from that, I will give the human resource to Africa, solving unemployment. And if I retire, having done all of this, I will be happy. I will be there.
Thank you very much. One last question.
And if not, what the business that is before they start trying to find it.
If program has no solution, there are programs that are not well posed. And
How does the student know that it's
the student has to understand mathematics. It is by understanding mathematics that you see that his equation does not make sense. It does not make sense to have this because the mathematics just driving. If you understand, you will realize that this is true, this is not. This is how it works. And this the understanding of the problem that allows you even to formally show that this is not correct. Yeah. Something is imposed if a space where maybe you want to find a solution. The solution does not belong to the right space. Or impose in the case it does not make sense to have a function of C1 alpha and an equation where you need two derivatives. So those are the aspects that we want to have. In this case, it does not make sense.
Thank you very much. Let's give a little big applause. Last time there were discussions on the first one. So we have a 15-minute break now. Please can I ask you to stand up, stretch your legs, run around the block, and be back in 15 minutes. Not African time with a big epsilon of 2 hours. Be back here at 15 minutes. And the start again at exactly 10:30.
Okay, it was not very funny to walk.
Yeah, but yeah, it was nice.
I told you, I bought this just now.
Yeah,
I need
yeah.
to use this. It's first time. It was actually the first.
Yeah. But
Please give me this.
okay.
It's what we are.
I have not forget.
Okay. From your, we'll try again. Yeah,
That's really interesting.
Thank you.
Okay.
Good. Thank you for having me.
Your,
Yes.
That would-
Because the resolution of your DIVA is so low compared to this. The resolution of the system is very low.
yeah, it's 1,000 by 700.
Now,
Maybe
maybe I just press escape for to see the screen.
Oh, okay.
I think F11. The point
Yeah,
there.
we should have.
It's okay. My problem, I will try to show two things.
Yeah.
The presentation itself, it is this one and this window as well. And so I have to make the following presentation without. You can go to presentation. And then,
Function F is presentation.
okay.
So you can switch on and off.
Yeah, but. And. Okay. Okay, and then I have to remove this and to show this. Then I have to go back. And again to the full screen. This is all what I want.
Yeah, it should be fine. We can even check it.
But if together with this thing, it's complicated. Let's try, let's start. Okay, now is the presentation.
Press escape.
I on, it's back. I press escape. What happens?
Yeah.
Scenes in the very round.
Yeah, it's because it's mirrored.
Okay. Just now.
Yeah.
Yeah.
Anyone you want.
I was having.
Maybe double video or
No, that is my computer problem. It's really a live
yeah.
presentation. Okay. It's not so bad. Okay, I can leave this. It's very big now, yeah?
Yeah.
So the demo, yeah?
The resolution of the.
Is there any- I can stop this. Go back. This is what I like. Yeah? Maybe it will work. And then with this thing, I now here. And it was terrible in the previous doc. You tried always too many buttons here.
But you know, used to it.
No, this is new. I bought this just. It's never used. This guy was the first using this device. You see it?
It's doing. This is moving a mouse. Yeah.
Yeah, but I don't like to have a mouse.
And if you.
I just.
If you touch the middle, it will.
It is a middle. It is a laser pointer. This is it works. But why? It's the middle of the left. Yeah. Yeah, it's moving. It is somehow a mouse.
Yes, it's an air mouse.
Yeah. I don't like this.
But you can turn this off.
I don't know.
This is everything.
Well, there's everything. Nothing.
Yeah.
So
So the
forget
only
it.
thing is not to move it.
Yeah, but usually if you have it in the hand, You have no chance. I will not.
Um,
I will remove this whole stuff. And you can.
if I put for you this one,
No, just here. This place.
fine.
Sure. Probably here, additional power supply.
No, that's
It's all the
just check that. Uh, 2.5 on my desk, to the left of my keyboard.
I have.
It's okay. It's okay.
It's okay.
There's something to protect.
Oh, now it's working. States, yeah. So I can go on, so. This way.
Voilà, já foi.
Ja, es ist nicht, kommt da nicht so klar. Weißt du. Ich will das nur klein machen, ob es geht oder wieder was ist. Weil ich da mein Programm starten will. Wahrscheinlich muss ich das rausziehen. Machen. Und hier reinstecken. Das ist immer so scheiße, das ist so ein unglaublich. Was für lächerlich ist das? Ja, natürlich. Ja. Das ist wahrscheinlich die beste Methode. Sobald das jetzt, gucken wir, was jetzt Auflösung jetzt hat.
Hoffentlich am Ende.
Ja, natürlich. Ja. Und das ist auch jetzt nicht richtig. Aber guck mal, das ist unscharf, das ist furchtbar. Ja, es ist. Also mein Computer ist zu gut für diesen Beamer. Es scheint ja aus Ursprungszeit.
Windows war ganz furchtbar, wenn man das anders eingeblendet wird. Aber ich habe den Eindruck, das liegt an der Fernbedienung.
Ja, das hat er nicht richtig gemerkt.
Ja, das geht doch jetzt.
Das geht. Aber ich will noch was außer Kohlen ablaufen.
Ach so, ja.
Dazu muss ich den Vortrag ausschalten.
Oh nein.
Und das ist natürlich
Das ist
Beamer
blöd.
beliebt.
Ja, ja,
und
klar.
alles.
Ja, das ist blöd.
Aber das werden wir schon schaffen.
Ja,
Das
klar.
wird die Möglichkeit gefunden. Ja. Also.
Wir haben uns auch schon getroffen, ne? Also, Sie kommen mir so bekannt vor.
Ja, wo haben wir uns?
Weiß ich nicht, wahrscheinlich bei Martin Bogates Feier oder.
Ja, das kann sein.
Ja.
Sind das alte Freunde noch aus Zeiten, wo wir mit ihm
Ja,
waren.
ja.
Viele Zeit in
Genau.
Deutschland.
Ja.
Ja, genau.
Okay, dann war das.
Ja, ja. Das ist wohl wahr, kann man so sagen, ja.
Das ist wie eine höhere Zeit. Weißt du, man schreibt aus seinem Gedächtnis auf.
Ja, mir hat es zum Schluss gefallen.
Ja, es war eine interessante Zeit, finde ich. Ich meine, es war beunruhigend lange Zeit, aber dann, als die da war, da ging es ja schon aufwärts. Aber also vor allem bei uns war es so, von einem auf den anderen Tag nur noch online-Leben.
Genau, und das hat er am Anfang noch ein bisschen kreativ genug gemacht.
Ja, ich glaube, wir sind völlig alleine gelassen
Ja, genau.
worden, also bis,
Ja.
bis ich die Ausstattung allein hatte.
Ja.
Also ich meine,
Ich war eine Kollegin Bautenschule. Praktiker wusste überhaupt nicht, dass ich mich da. Und ich als Mathematiker, ich habe das dann nach 2 Wochen
ja klar.
Und die nicht. Ja.
und die nicht.
Ja, ja.
Und das wissen die Studenten heute noch.
Ja, natürlich. Also ich weiß noch, es war ganz interessant. Also ich hab ein Skript gemacht, getippt, das Sie auch
Ja.
dann hatten, und habe dann die Vorlesung so gehalten, dass ich auf dem Tablet annotiert habe. Also ich habe Beispiele gezeichnet, sogar, also dass das Lebendige rüberkommt. Und das alles aufgenommen. Das war natürlich furchtbar viel Arbeit. Aber am Anfang, also auf dem Tablet, wenn man da schreibt, macht das ein kleines Klickgeräusch.
Ja.
Wenn man also bei den internen Lautsprecher das macht, klingt das dauernd. Das
Ja.
ist nervig, das kann man nicht ertragen.
Ja.
Also brauchte man so ein Headset.
Ja.
Aber zu Anfang der Corona-Zeit gab es 2 Sachen nicht. Und das war Toilettenpapier und Headsets. Weil die natürlich alle das so machen wollten. Da habe ich ein ganz altes Ding geliehen, das zu machen. Und ein paar Wochen später hatte ich dann ein Headset, ein eigenes. Aber das war interessant. Aber das hat mich wirklich 7 Tage die Woche, ungefähr 10 Stunden am Tag
Ja,
gekostet,
das
diese
hat
blöden
man-
Videos zu
Ja,
produzieren.
das hat man-
Wenn man das ernst genommen hat, war das unglaublich viel Arbeit.
ich war schon immer so, dass ich modernste Technik ganz gerne benutzt.
Ja,
Und
ja.
meine Kollegen hatten einen sogenannten Michelin-Verein.
Ja, das haben wir auch. Ja,
Ja,
ich auch. Ja, okay.
Ja, also dieser
Ja, ja. Ja, ja.
hatten wir andere Kollegen, bei den Bauingenieurkollegen. Und wir haben so eine ganz gute Verhältnis gehabt. Und das ist Schreibsoftware. Schreibsoftware. Ganz vieles geschafft und habe im nächsten Semester dann in den Ferien gelernt, wie man ganz ordentlich schreibt und dann regelrecht trainieren müssen. Und dann habe ich die Vorlesungen live geschrieben und aufgezeichnet. Und dann hat sich das Aufzeichnen perfektioniert und habe ich alle Vorlesungen nochmal gelesen, für mich selber zum Aufzeichnen. Die Studenten sagen mir, ihre Vorlesung, das ist ja prima, viele arbeiten nicht und können sich dann das alles
Ja, klar.
ganz
Ja, ja.
Und das Beste ist, der kann so ausschlafen. Das habe ich auch.
Ja,
Gemacht. Das kann ich ganz gut.
Ja, ich habe so viel aufwendiger gemacht. Also nicht nur das Abfotografieren. Ich hatte ja auch so ein System mit mehreren Beamern und konnte dann, also wir haben einen richtig großen Wagen, so einen Bildschirm, auf dem man schreiben konnte. Das war schon ganz gut. So habe ich es nicht gemacht, sondern also diese Spontanität wirkt in dem Video ja auch dann merkwürdig, weil man natürlich eigentlich spontan ist in der Reaktion auf die anderen. Da habe ich halt das annotiert. Das
Deswegen habe ich
hat aber das Schneiden, das hat gearbeitet. Also ich habe danach die Rs auch alle rausgeschnitten und so. Aber da muss man halt dann einmal die Sachen zu machen, vielleicht 4 oder 5 Mal drüber
Ja.
gehen. Das ist richtig aufwendig.
Das habe ich auch gemacht, wenn ich mich vor mich selber geärgert habe.
Ja, und dann haben wir noch so einfache Quizaufgaben gemacht, die nur dafür da waren, also selbst automatisch korrigieren,
Ja.
dass die Studierenden wissen, ob sie ungefähr verstanden haben, worum es ging.
Ja.
Also ganz, ganz einfache Sachen. Übungsaufgaben und all sowas, aber das war ein
Das habe
Aufwand.
ich auch gemacht.
Oder weiter? Okay.
Wahrscheinlich.
Yes. Everyone, thank you for all being back with absolute mathematical precision. This is really impressive. It's miraculous precision. I'd like to introduce our next speaker to you, Professor Sergei Rozhanov. He is a full professor of applied mathematics at the University of Saarland in Saarbrücken in Germany. He has an extremely illustrious research career. He's published many books and monographs. And some of these research interests include the following. He's really interested in long-range interactions and the simulation of long-range interactions, which I hope we'll speak about a little bit. It's about interactions between things like particles that are extremely far away and how to numerically model these super long-range interactions. And he says that these things pose severe challenges for numerical systems. The other exciting research area that he's involved in is the numerical simulation of high-temperature superconductors. So I don't have this will feature in his talk, but he's got some very interesting results on how to combine Euler and Maclaurin series expansions with Fourier methods, provide really interesting numerical approximations and solutions for long-range electron-electron interactions in high-temperature superconductors. Now, we've got some research areas that span plasma simulation, for instance, and he's also very interested in expert in Boltzmann equation and numeric solutions of Boltzmann equations. So the field of numerics, solving Boltzmann equations, is a particular interest of his. He holds a diploma in mathematics from Moscow State University and a PhD from Sheffield University. So very welcome. We look forward to a really, really interesting talk. Welcome to Starfield again.
Yeah. Thank you, Ulrich, for your kind introduction. Thank you all people for coming to my talk. I'm really blessed to be here. My second talk at the AIMS. The first one was about 11 years ago. I was here visiting just one day, giving the talk. Now it is more serious. The world of particles, my talk. But just the outline of the talk, and I would like to present our research activities in last years a little bit more detail, really a little bit more. And then we are going to speak about interacting particles. Mathematical description of this should be the equation, Kramers equation of Boltzmann, one of the most complicated and interesting mathematical objects over all areas in mathematics. Then I will make some historical remarks on this equation, and then we are going to numerical skills. I will present very famous DCMC, direct simulation Monte Carlo procedure to solve this highly dimensional very complicated equation on a really reasonable, simple way. And I hope if all electronic equipment will work to show you just live solution of the Boltzmann equation for really a reasonable problem. And then generalization of this method, which is actually now about 60 years old. Direct simulation Monte Carlo introduced by Professor Björk from Sydney in Australia. It was our research stochastic weighted particle method. This is simple generalization which produced a lot of theoretical and practical questions. And at the end, we have written a Springer monograph just to prove that this generalization, how it is connected to classical method and how it is connected to equation itself. And at the end, as I already mentioned, I will show you a numerical example. So, my group in Saarbrücken, we are dealing really with real world problems. Boundary element methods for partial differential equations, that is the main topic. I'm not going to speak about this topic today, but there are a lot of applications in acoustics. Just last PhD 2 weeks ago was defense to this very interesting thematic in the fall. Our live acoustic is very important, protection of the sound from the autobahns, you know, everything. Electrodynamics, all my life. I was a student, I have written my diploma thesis to electromagnetic scattering problem in Moscow at this time. It was already very, very applied research. And up to now, just 2 days ago, I was visiting my friend here in Stellenbosch. He's working in a company and working on electromagnetic software, and we are, you know, each other since 15 years. And one of my PhD students did really results of her research was improved software of this company here in Stellenbosch. We have done 3 PhD theses in biological protein simulation, 2 of them in biological informatics or computer science, and 1 in mathematics. Many years I was working with engineers from Aachen Technical University in incremental metal forming. And at our university in Saarbrücken with biologists and physicists in the surface finite element method, which is very close to boundary element method, modeling red blood cells. These really physical experiments, and you know how important it is. And again, it was one PhD thesis about this. And the last time, we mentioned already, one of my PhD students, since 2 years, about 2 years, he is now my postdoc. Maybe he did really a breakdown in the computation of high temperature semiconductors. We will see. It is really, now we have got in PhD position, an application was successful, and the PhD student will start in December. And this position is from German agency for aerospace, DLR. Yeah, we will see how it will work. And the second part of my research, it is completely different, and I was able to survive somehow in both communities which do not intersect. The only worldwide intersection was Saarbrücken. I was organizing 1 year meeting kinetic theory, this one, and 1 year other year meeting on boundary element equations. This was the previous applications. And most famous Boltzmann equation, we will see it very soon. And granular flows, a lot of applications, gas mixtures, plasma simulations. There's now interesting contacts with the Plasma Institute in Munich and Greifswald maybe in the next future. And again, semiconductor simulation. This topic somehow connects the both research. Okay, let's go on. What are particles? I decided to take these 4 examples. Particles can be helices. And so they fly in our universe. They are big particles. You cannot imagine how big they are. And they interact with gravitational force. And the mathematical model for this, it is a famous Vlasov equation connected with the Poisson equation to compute the gravitational force. And 30 years ago, it was about 30, a little bit more. It was proved that there are global solutions of this system of nonlinear, very complicated partial differential equations for the Cauchy problem. If you start with a smooth data, the solution will exist all the time. It was mathematically a perfect result, but it was a disaster for all of us because we always suppose that this system is able to describe the concentration of matter to the black holes. But it was not. It was proved that the solution remains smooth in the sense that derivatives exist and they exist all the time. No black holes. Interesting. Think that about 25 years ago, we remembered that there was a paper in 20s, about 100 years ago, of Bulgarian physicist Manev. And so we changed a little bit, he changed a little bit gravitational potential with arbitrary epsilon, stronger, a little bit stronger. And so immediately you have a black hole. It means that this Coulomb potential in electrodynamics and gravitational potentials are of the same kind, of the same singularity. They are somehow on the boundary. And so it is why the real world is so complicated. It's not stable, but it is not unstable. It is in between. If you have a small change of your gravitational potential, immediately your equation will produce singularities in the finite time. Yeah. Second example, it is coal particles. It was also a big project in Dortmund modeling power plants in Germany. And the coal power plants, they're extremely nice, extremely effective in ecology. And so transported these particles for the burning. It is a complicated mathematical stuff because they are transported pneumatically with a lot of pressed air. And for this, completely turbulent flow. Three-dimensional turbulent flow you can describe by the system of Navier-Stokes equations. And it is complicated already for itself. And then that is a system because the particles interact with collisions. And the collisions are inelastic. It was one granular flow. It was one of my topics. And so we did this simulation again, ending in PhD in publications with the University of Dortmund in Germany. Now plasma. Plasma, for example, electron plasma. Here, the particles are really microscopic. You don't know a lot of them. You cannot see. These particles you can see. These particles is a photograph of galaxies. Yeah, but this you cannot see. They are so small electrons, but they interact with electrostatic potential, which is actually up to the sign the same as the gravitational potential. But in our talk today, we are going to speak about very simple particles, just billiard balls. Let's assume that this air in this room is filled by billiard balls. They are small, ideally elastic balls, and they fly without interaction, free on the straight lines, naturally, second law of Newton. And suddenly they collide. They don't know about each other just before collision. And in the collision, they change velocity. And that is the interaction. No collisions at all, up to the, no interaction at all, up to the collision, and then change the velocities by the collision. What is the equation for this? And this is very famous. Now we are coming to some formulas. It will be not so many in my talk. But the most famous Boltzmann equation is written here. Actually, it is simple. Eh? There are only, I think, less than 10 letters. Unknown is a function f. This is a time derivative. This is a velocity variable, three-dimensional. And it is gradient with respect to x. It's again three-dimensional space variable. And so on the left, you have very simple transport equation. Very simple transport equation. It means that the particles fly with the velocity v without any change of the velocity. The position is changed correspondingly to the straight line length. And then, what is really interesting, it is this right-hand side. Right-hand side of the Boltzmann equation is so-called collision. How to describe the collision of two PR balls? Yeah, that is not so trivial. In any case, the unknown function f, it is a function of position x, three-dimensional, velocity v, three-dimensional, and it is time dependent. It means equation is so written is quite simple, but it is equation in six-dimensional phase space. The physicists call it space, the phase space. This space variable and the velocity variable at the same time, and time dependent. Usually x in some computational or realistic domain, and velocity v can be arbitrary from R3. And what happens by the collision? What is the interpretation first? What is the interpretation of this unknown function? This unknown function is non-negative, and the best interpretation for this function, it is a probability density from the modern mathematics, which is not available, was not available to Boltzmann in 1872. The whole probability theory was developed much later. At this time, he calls this distribution function. But now we know it is a density of a distribution function. And very rough, maybe explanation of this function is as follows. The function f gives you the probability of the following event. At time point t, at the position x, there's exactly one particle flying in the direction t. That is the explanation. Yeah? And so, if the particles collide, then we have two particles. I don't write t and x here, it will be too much. But it is important to write the velocity variable. The f describes the probability that one particle is here. You have learned already the probability theory, at least a little bit in your study. Yeah? And you know, if two independent events, in our language, molecular counts, and then the probability of both events is just a product of probability. And then we multiply the probability of the particle to be at x with a velocity v and w, that is a product of the both. Only if they collide, the velocity v is of course lost. Yeah, a new velocity will appear, which is a gain here. That is this both prime velocity. Where are they coming from, these complicated things? They are not really complicated. If you add the both velocities v and w prime, you can see you will get v plus w. It is conservation of momentum. Yeah, of course, we have two particles before collision and we have two particles after the collision. It is conservation of mass, it's trivial. And conservation of momentum is written here. And this term describes the conservation of energy. Because we assume that the particles in the Boltzmann business are completely elastic. They do not lose the energy by collision. Yeah? And this is the form. And again, think a little bit if one particle is sitting here and the other particles come. The collision can be a central collision, and it can be at the end tangential, and everything in between. So this parameter E describes exactly this situation. It is from the unit sphere. And the velocity W can be arbitrary. That's all. That's the famous Boltzmann collision operator. Here we have a loss term, and here we have a gain term. These two velocities will disappear after the collision, and these two velocities will appear. And the probability of such a collision, it is a collision kernel of integral operator of this type. You see, this is nonlinear operator because the function f is here the product. But it's not very complicated, it's quadratic. So it is a reason why we write this term q of f, comma f. It is quadratic. And from a mathematical point of view, you immediately generalize to bilinear operator. You take two functions at the g here instead of one function, and so it is a generalization to bilinear operator. Again, everything together. We have transport term on the left and collision term on the right. And this is the famous Knudsen number. It is a dimensionless scalar number only, which describes how dense is your gas. For example, if your aircraft is flying in the free space, then this Knudsen number will be more or less infinity. There are no collisions of particles in space. There are no particles. And then the space shuttle is going down. And at the height of 70 kilometers, this Knudsen number will be about 1. It means the shuttle is maybe about 10 meters. And the collision happens also in the range of 10 meters. It means how long is the mean free path between the collisions, and your object is important in this business. And with this ratio, this dimensionless, it is a Knudsen number. Here, if you are sitting in this room, the Knudsen number here is 10 to the power minus 3 if our objects are chairs or here the human beings. And if you consider even in this room something production of microchips, they are so small now, then it is a gas is here is not rarefied, but the dimension of the object is also small. And so again, this Knudsen number will be about 1. And so this term will be extremely important. Okay, here are some models of the interactions. They are all of them, the most general one, inverse power potentials. Depends on the relative velocity of colliding partners and of the scattering angle. Complicated thing. Exception is here already realized 150 years ago by Maxwell himself. That is, if you take this interaction potential m equal 4, then this dependence disappears. And it is somehow, if you know a little bit about differential equations, they are complicated equations with variable coefficients. And they are simple equations with constant coefficients. And so it is exactly this analogy. Somehow this Maxwell case corresponds to the differential equations with constant coefficients. And there is some analytical solution of the Boltzmann equation, non-linear in this case. Further simplification is if you assume that this scattering part is constant. And most famous part, if this interaction potential goes to infinity, you will go to the called Hart spheres model. 99% of all realistic simulation will be done with this model. Yeah, Hart spheres, exactly Hart spheres. Now, in the modern mathematics, if you deal with especially partial or integral equations, partial differential equations or integral equations, what is most important thing, it is weak formulation of your equation. It means you take your equation, this transport part is more or less trivial, we take only the collision integral and multiply this by a test function and integrate over the whole space. That is the usual business in studying partial differential equations and integral equations in the space, in some functional spaces. An interesting consideration was already done, this result by Boltzmann himself. Then if it is 0, if it is exactly 0, there are only 5 functions. There are only 5 functions for this: a constant, conservation of mass, all 3 components of velocity, conservation of momentum, and d squared, conservation of energy. And that is important. And the second important factor, already detected by Boltzmann himself, if the integral itself is a function of v. But if it is 0, then there's only one solution of this nonlinear integral equation. You can consider this, find a function f which fulfills this homogeneous equation. And the solution is a so-called Maxwell distribution in the physical language. And for you and for all mathematicians, it's just a Gauss curve in three-dimensional space. And T is here in physical space, it is a temperature. And capital V, it is a mean velocity. They are only found the density can be here instead of 1, can be density. As only these three functions, density, temperature, and the mean velocity, actually 5 functions because the mean velocity is a vector. Yeah, they describe this distribution. And this is really famous. Okay, and this is so-called H theorem. If you take the Boltzmann distribution function, it is non-negative. Assume it is strongly positive and take a logarithm of this and integrate over all variables. It's only not with respect to t. We will get a function of t. And this function was called H functional, and it cannot increase. It is always decreasing. And this fact produces a lot of troubles in Boltzmann life, because in his time, it was assumed that the nature is reversible. But this inequality shows very clearly it is not. Once the relaxation takes place, it will never come again, never come back. It is a contradiction to classical mechanics. If you take n particles, let it move, stop. Change all velocities back and wait. They will come to initial configuration back, reversible. And Boltzmann collision is not reversible. It's clear. The number of particles goes to infinity. That is some limiting process from modern mathematics. Is not a wonder that it can happen some strange things. Okay, I show you now. It's difficult to see on this a little bit. Here's a stream of 2 particles having velocity at the x-axis 1 and -1. And then there's a relaxation. You see 2 separated velocities. Particles are going, one part of particles is going from left to the right, and the other from right to the left, and then they collide. What happens? At the end, we have a maximum for Gauss. Distribution will be. That is the main job of the Boltzmann equation, to try to produce equilibrium everywhere. What is the connection to real world? Nobody is interested to see the function of 6 variables time. What can you do with this? You can even not, you cannot plot. This plot in the slide before was plotted without x in one position in it, and without third component of velocity. So you can plot 2-dimensional function. But the connection is very simple. If you integrate over all velocities, you will get the density of the gas. Real physical density. How many particles are inside of the cubic centimeter? If you multiply your distribution function by velocity and integrate over all possible velocities, you will get a momentum. And this tensor is a flow of momentum. It is 3×3 matrix. Tensors. To scientifically for this stuff. And this vector, it is flow of energy. And if you have these all things, you can describe your flow completely. You have stress tensor, you have mean velocity, you have heat flux vector, you have everything. If you know the distribution, just by integrating the simple procedure, even numerically. So, a little bit to history. I already mentioned that this very important parameter is a Knudsen number. If this Knudsen number tends to 0, then the gas becomes dense and dense and dense. And we know since Euler that to describe gas flow, it is possible without having the Boltzmann equation. Possible to describe this, you were using classical energy numbers, something like a system of Euler equations, or not? They are known since the 18th century. Yeah, conservation of mass, energy, and momentum, nothing else. And so it was a Hilbert who realized two important things. Try to look for a solution of the Boltzmann equation in terms of power theory corresponding to this small parameter. And so he assumed that the solution is analytic in this small parameter. It can be written as a power series with some coefficients Fn, which are still functions. And if you see, here's this 1 over Knudsen number, and here's the Knudsen number to power 0 at the beginning. Here you have 0, or the first order is 0, and here is a negative one over Knudsen. So you have to assume that the 0 function from this Hilbert decomposition should fulfill this equation. And you immediately know from Boltzmann time, yeah, it was 40 years later, done by Hilbert, then the solution should be Maxwellian. Only Maxwellian distribution can fulfill this equation. And if you put this inside of the equation, the next one will be this. And you see, F not assuming that is already given, Maxwellian. Then it is a linear integral equation. Because now it is bilinear, and F naught is known, and we are looking for F1 in the next step. And F1 should solve this linear integral equation. And at the time of Hilbert, 110 years ago, actually, it was Fredholm theory was very new. And so he realized, look at this, here's a linear integral equation for F1. And here's the right-hand side. When we know from Fredholm, the right-hand side should be orthogonal to the kernel of operator. On kernel of the operator, there are 5 functions. Constant, velocity, energy. And so multiply this right-hand side by these 5 functions and integrate and force the orthogonality. What is the result? The result. Okay. Yes. First, I have already. Yeah. The result for F naught, we have to look for the density, velocity, and temperature, and we force them. That I told already. And then there is the result. It is complicated system. It is really hard thing. It is system of Euler. Known since century. 250 years. And it is exactly Fredholm condition for solvability of the first term in the Hilbert expansion for the Boltzmann equation. It was a really funny result for Hilbert, and has reason. One of the best applications of the Fredholm theory and this connection between real world particles and this completely mathematical thing. Fantastic. And immediately he tried to get Navier-Stokes equations. They were already known as this. He thought the next step will be to compute F2 in this, and it should give us Navier-Stokes equation with a heat flux and so on. But it was not. It was it was not. The assumption of Hilbert that the function is analytic in Knudsen number was wrong. And so independently, Chapman and Enskog, 2 years later already after computation of Hilbert, find out the system of Navier-Stokes equation on a little bit different way. And they assumed that the function, this analytical dependence of the Knudsen number should be removed. And then it is possible with some tricks. It takes me 2 lectures if I teach this. It's not so often I'm teaching really kinetic theory, but it is about 2 times 90 minutes to show you how to the system of Navier-Stokes equation. This is completely compressible, 3-dimensional system of Navier-Stokes. Do you like to get $1 million bucks? Who is interested for this? Just try to prove the existence of the smooth solution of the system. This is one of the millennium problems formulated in 2000 in the Clay Institute in Boston. But to tell you the truth, I hardly believe it is much more methods to get $1 million than the proof existence of a Navier-Stokes system. It's much easier to do something different. But however, I know one guy from London doing this. He's sitting in the evening and proving the existence of the Navier-Stokes system in this. But you see, that is most famous description of the fundamental equation for the fluid dynamics, Euler system and Navier-Stokes system. They are only zero in the first terms of the Boltzmann distribution. So complicated. Okay, now a little bit to the theory. Of course, that the matter is of particles we know symplectic type. And most famous in this business is, of course, Maxwell and Boltzmann and Hilbert and Harald Rath and Carlo Cecchiniani from Politecnico Milano. He died, unfortunately, 10 years ago. But I was really happy once to have him in Saarbrücken maybe 5 years before, in 2005. And I was visiting him as one of the most famous guys in this business connected to the Boltzmann equation of our time. Carlo Cecchiniani. So again, if you take original paper of Boltzmann from 1872, it takes 5 lines to derive the Boltzmann equation. Something like what I told you at the beginning. Here is a particle flying, a minus, plus, everything written. Yeah? But a mathematically rigorous derivation of the Boltzmann equation for the classical mechanics with all proofs of this limiting process, it takes 65 pages in the book of Cecchiniani, Illner and Pulverenti. You can buy this book by, or maybe it is in your library, by Springer, and you can read this. 65 pages mathematical proof for this. Fortunately, we have some analytical solutions of the Boltzmann equation. And one of the most famous guys here is Alexander Bobelev from Moscow, Keldysh Institute for Applied Mathematics. And he was visiting me many times, once for whole year. He got a position as a professor supported by German academic exchange. And later on, he was many years professor in Sweden. So I was visiting him there. I don't know Kruk and Wu, it was almost the same time. Existence theory, of course, for mathematicians is essential to prove that the solution of this non-linear equation exists. There are names of Karleman, Archirid, I know him very well, from Göteborg in Sweden. Nina Maslow died, she was from St. Petersburg. Bernd Wernberg in Göteborg as well. And Cedric Villani, I know him from the conferences. It's not really a close connection to him, but he was the second Fields medalist, yeah, on the field in the last 30 years in the field of the Boltzmann. And existence theory, in general case, it is my friend Reinhard Illner from Victoria in Canada, Chinbrod, Di Perna died already, and Lyons, famous Lyons, that was the first Fields medal in the field of the Boltzmann equation. Again, like Archirid and Anna Nouri from Marseille, all very known persons in this business. So interesting, we are now speaking about history of the Boltzmann equation. Here's one paper from London Royal Society from 1867, 5 years before Boltzmann. And here, it is a paper by Maxwell himself. And here is written, look at this, it is exactly Gauss distribution. What is written here? He was already very close to derive the Boltzmann. And he writes, then this distribution of velocities will not be altered by exchange of velocities among the molecules by their interaction. It means that it is equilibrium, it stays. Yeah? They change velocity, of course, by equilibrium, but the distribution remains the same. And this is therefore a possible form of the final distribution of velocities. Okay, it is also the only, that is the main sentence of this paper. That is the only form. It was no proof for this. Proof is quite easy in the classical setting. And this is very famous book now, written by Carlo Cecchiniani from Politecnico Milano, about Ludwig Boltzmann. A lot of mathematical formulas inside, but whole life of Boltzmann is written here. And his life was very successful. In this, my first slide is the Boltzmann equation. He was a real photograph from 1872. He has got his first professorship in Vienna for mathematics, not for physics. And he was at the age of 28. Huh? Try to get something like this now. To get a full professor in Vienna for mathematics at the age of 28. And he moved to Graz after that, and was very happy with his life in Graz. And then it was some troubles with Germany especially, and with wars. Okay, it's no time for this. If you like, I can tell you in the break. And he went to Munich and Leipzig, and finally back to Vienna. The second time he was completely unhappy, and finally the end is suicide. Suicide in Italy, in the holiday, in this place. Very unhappy. And okay, numerical schemes. They are really Monte Carlo schemes. Is of course it's stochastic. I was teaching a course about this. Monte Carlo method solving integral equations, differential equations, even linear system equations you can solve by Monte Carlo. But what is a very simple interpretation? If we have some computational domain, we divide it in spatial cells, like in finite element discretization. In every cell, we don't consider x. The function, we assume function is constant in x over the cell. And so it is function of t and velocity variable only. T is of course positive. And from a mathematical point of view, particle scheme for this, it means we approximate this continuous density by a system of Dirac layers. They are concentrated on velocities of particles in 3 dimensions. And that's all. And all particles are equal. That is normalization factor is just 1 over n. And what is important to approximate the initial measure, there's of course it's a matter of stochastic numerics. Given initial distribution, produce a system of random numbers corresponding to this distribution. Very classical problems, a lot of solutions for different settings. And then the particles have to collide. And they are discrete events with some waiting time, which is in Boltzmann setting called time counter. That is a random variable with this probability. And then this probability is one of the most important connections to the Boltzmann equation. It is connected to the Majorant of the collision pattern. How often the collision takes place? Here is a Knudsen number involved. That's very simple simulation. And here's one tricky thing. If you consider Hart-Spheres model, which is 90% of all simulation, then the probability of collision is proportional to the relative velocity. And so we have to choose from our set of velocities 2 particles randomly corresponding to this discrete velocity. It is not an easy task, and it should be done in an efficient way. But it is clear how to do this. And then, if you know already your collision partners, you choose randomly on the unit sphere your collision parameter, the angle, or unit vector from the unit sphere corresponding to this distribution of unit vectors of the unit sphere. And this is again classical task, no problem. Just to choose a random vector from the unit sphere corresponding to the given probability. And then you proceed to collision transformation, new velocity. And you wait again a little bit, and then you collide. You wait a little bit, and then you collide. If the sum of all these waiting times exceed delta t, then collision process in the cell is over. And you move your particles free flow corresponding to their velocities after the collision. And so they cross the boundaries of the cell, and so the whole story begins from the very beginning. Now you have new particle in the cell, you have new everything, new velocities, new distributions in every cell. There are millions of cells, of course, in three-dimensional setting. Even in two-dimensional, it can be 100,000 or more cells. So, and generalization of this process is, of course, to introduce weights. Instead of the particles only dispositions and velocities, we, together with my partner Wolfgang Wagner, who is retired now from Weierstrass Institute for Stochastic in Berlin. Yeah. And he was actually the first who was able to prove the convergence of the classical direct simulation Monte Carlo scheme to the Boltzmann equations, numerical scheme, convergence in the sense of weak convergence of probability measure. Here, as you see, Boltzmann equation is physics. We have hydrodynamics, classical, Euler equation. We have Hilbert expansion. It is classical analysis more or less, yeah. And now we have a very strong connection to probability theory, stochastic differential equations, and everything. And introducing weighted means that the particles are unequal. What is interpretation? Interpretation is the real number of particles is 10 to the power 23 something. Impossible. Now we are doing simulation with 10 to the power 8, 10 to the power 10 on the big computer. On such a laptop, 10 to the power 6. Okay? And then every of these numerical particles should represent enormous amount. And so it is easy to think that one particle represents so much, and the other particles less. And then if they collide, only part of this representative collides really, and the other part will not collide. And so we take some weight. We weigh from the weights of the particle and introduce two equal particles of the new weight. The problem here, it is now at the beginning we had two particles collide, two particles going away. Now two particles collide and we have four particles. That can be very useful if you are dealing with very rarefied flow somewhere. When only few simulation particles reach some region, and suddenly they try to reproduce themselves, and so we have more and more and more. And if you have more particles, you have less variance. And the whole Monte Carlo numerics, more or less 90% of all fighting in Monte Carlo numerics is to reduce the variance of your numerical scheme. Yeah, to get less and less variance. Okay, and this theory of this Monte Carlo scheme and generalization is written in this Springer monograph together with Wolfgang Wagner from Berlin. And it was a lot of work, about 15 years, summarizing everything this year. The theory and a lot of numerical examples. A lot of numerical examples for this. Okay, before I show you a numerical example, what is now? What is going on today? My actual co-authors is Irena Gamba from University of Texas. More from theoretical point of view, she is very famous in kinetic theory now. And this is alphabetic order of my part, but not chronological. We are working together since 25 years. And this Andrew Hong from Sandia National Laboratory called me, or had written an email to me just 2 months before this meeting here in South Africa, and asked me, I try to introduce your weighted scheme for some problems of Sandia National Laboratory. You know, it is one of the biggest research institutions in the United States, mainly 2 places in New Mexico and California. And Andrew is sitting in Livermore in California. And now, I think next week we start real cooperation. Exactly for this, variance reduction by Monte Carlo simulation of Boltzmann equation by the use of weighted particles. It's not constantly. Thorsten Kessler is working now in Idaho. He's got his own European project in research for the Boltzmann equation in modeling of microchips production. You know, Eindhoven, maybe it is not so known, but it is ASML, one of the biggest that's only one actually, producers of machines which are able to produce microchips. Yeah. And it's exactly this connection to the real world, not a space shuttle, not a vacuum pump, but just production of modern microchips. The so rarefied, this is not normal atmosphere there. They are working with rarefied hydrogen exclusively. I don't know exactly why it is hydrogen, but in this atmosphere, they are working with exactly Boltzmann equation. And this research he applied for this is my PhD student. Now, since 1.5 years in Eindhoven. On George Wiki, this is interesting because he is in plasma laboratory in Princeton. But at the same, he is so interested for Boltzmann equation, especially for these papers which we have written with Irena Gamba together. And the last paper with him is appeared just in July this year. As they are really my current collaboration partners. And so I will try now for the numerical example. Which is so now this is a really demonstration tool. This one I have written some years ago together with our book about Boltzmann equation, just to be able during the lectures to produce some numerical results really in lifetime. You see here the Boltzmann in the age of 28. You can choose some computational domain. For the presentation, it is really not important to have some microchips. It is not interesting geology. What is interesting is space shuttle. Or you know, now even tourists are going into space, for millions of dollars. And so by landing, they're sitting in such an object, and it is fire over the poles. This thing. And this is interesting to computer. It's necessary to protect people by landing or scientific equipment, whatever, from this fire. And now we have, in this example, we have a shuttle. You see the Boltzmann equation with some physical parameters. You see this collision transformation, some initial condition, boundary condition, that's all. Not so important, and we run now this simulation. This is a flow over the obstacle. The number of particles for this simulation is about 1 million. We plot some of them. And every 10 time steps I plot new. It is development of the flow. Now it is, of course, time dependent. After a while, it will be stationary. And this is supersonic flow. Now we see only the particle. One portion of it, maybe 1% or less. But what is important to see the density, physical density. And what you see here, a lot of fluctuations. Typical Monte Carlo simulation. You have a lot of fluctuations which will disappear after a while. They begin smooth. And you know, to take average in Monte Carlo seems it is most important thing. The average always converges to the right value. And so, you see all of it. Density is now much better. And the scale here, it is up to 6. Here's 1, and here's 6. It means the density increases by factor 6. It's not dramatic, it's okay. Density is okay. And the Mach number on this height, it is about 10. This height of 70 kilometers. Normal aircraft is flying about 1 Mach and less than 1 Mach. It's subsonic flow, but close to 1 Mach. And this is Mach number 10. It's completely supersonic flow. and you see them with this Mach number. Here's the gas more or less undisturbed on the left in this region, and behind the body it is slowed down. This is an interesting picture, and you see here stochastic fluctuations on front of the shock. They should be removed naturally. Yeah? You see sometimes one of the particles is coming through. Clear. Most important picture is this one. Most important picture is this one. This is the temperature. And temperature is increasing up to 3,500 from 1 hour. And so it is burning everything. In reality, it is not so high. In reality is not billiard balls. They are billiard balls. Not here. Reality is so that you will get plasma. And a lot of energy is going in ionization of your gas. And so the real temperature will be less than 3,000. But still very, very high. And you need additional protections. A lot of science to produce this protection of your landing body with a height of 70, 60 kilometers. Okay. I think we can stop this now again. My last slide. If you give a talk, it is necessary to think about different things. Yeah? How it will be, what is the audience? And now we are here in South Africa, and I think it is a very funny place, and it is necessary to finish my talk with some poem. And this poem is written by a Danish mathematician, Piet Hein, from 20th century. It sounds metal seems is the popular name for milliards and milliards and milliards of particles playing the infinite game, billiards, billiards, billiards. Thank you.
Thank you very much, Professor, for this very insightful talk. We have about 5 minutes for audience discussions and questions. So let's start with 1 or 2 questions at the back, and then 1 or 2 student questions.
I thought this book very impressive book. My opinion was the word of mouth, very general. Yeah, topic. Now, if you look at the development of possibility theory in the last decades, I mean, in the context of Boltzmann equation, we explained Gauss distribution, which comes as a universal result in universality theorems, probability theory everywhere. Yeah. And now in the last couple of years, the interest has moved to other types of universality, like space transitions and also the KPZ universality. Have you encountered also this type of? Yeah, I didn't mention this, but a little bit, but not mathematical, with this mathematical treatment. Yeah, I mentioned granular force, inelastic collision. If you have inelastic collision, there's no action distribution with that. We have written a paper about overpopulated tails of the distributions in this case. That is my experience in non-maximum distribution. If you change billiards to something a little bit different, then you will immediately get to different physics and different equilibria, if any. For example, pure granular Boltzmann equation, the last final state of this is just a Dirac delta. Everything is frozen. Very simple, but can be considered still as some limiting process of a maximum distribution. But overpopulated tails, for example, in thermal gas, if your particles collide inelastically, they are no distribution. But if you put heating on this, you can produce arbitrarily complicated equilibrium distributions, which are not constant. This is my experience in this study, non-Maxwellian equilibrium.
Yes, Musa.
You mentioned how but the reality from the example in the show, the atmosphere we have. So how would you this?
In one of the initial slides, it was mentioned a mixture of that. Of course, if you consider Earth's atmosphere, there's not enough to consider only one. There's always a mixture. And then, if you assume still for every component of the mixture, if you assume there are still balls, different diameter, different mass, then you have to consider a system of points on equation. And it's usually the case. It's much more complicated. Yeah, it is a system. It is they collide. The collision integral is the sum of them. Every particle is every another. A lot of people. That is a mixture. Of course, assumptions that the idea of balls is okay. Fortunately, all physicists, and especially people from aerospace engineering, yeah, they accept this. It is okay. Because what they can consider in experiments, and they're really big experiments everywhere in Japan, and the United States, and Europe, it corresponds quite well to the reality. Yeah, for low temperature. If the temperature is something like in my numerical examples, these are ionization sites. And so is plasma. It's again completely different physics and completely different description. You know, as I was young as you, it was always a sentence: if you study fluid dynamics, gas or fluid, or solid mechanics, everything is easy. Don't deal with plasma. You will get crazy.
I guess everyone could.
No, I think it's so much very good, presentation. So,
Boundary motion is one part of the business, of course. All simulations here. Again, if you consider gravels, they collide in elastic. In every collision you lose it. There's an interesting thing to put this in the thermal mass. The thermal mass is some medium where the particles we don't describe them. By the move corresponding to the volume. And so we have interaction with the background, which is growing, and your real particles which move on some trajectories of the light. And there are two particles, the background and conditions. And so it is more complicated than some things. Very interesting. Rolling motion can be involved. This is not so easy, but reasonable. And you consider something that is around you and leaves corresponding to means particles are alive, that the particles then during the heat flow, they are not staying and get peaks. There's no additional energy to be moved, and then for all the process of all the data distribution of the it's the graph. Just software, this high software, not distributed but if you try to distribute the medium to get the medium documents, it's happening in the work and so it's complicated. But of course, it's like that. Students, when ask the students, they already, or even the real public. But I don't know if it's some people are doing this. It's essentially no line That's what we all software. Yeah. But it is actually all background is written in form. Yeah, and this graphical interface is you can see here. Everything that I do myself.
You can I follow.
Only memory management is written in C. It was Fortran is the original term. But still it is fast and language.
Did I follow the question? Then we've got a student question at the back. I'm really interested in the stochastic weighted particle method. And do you have any intuition why you get the reduced variance in your estimate? So everyone, the background of the question is often when you run a Monte Carlo method, you have an unbiased estimate. You can prove that it's unbiased, but the variance is so big, you can actually not really use it. Why? What's the magic?
I will explain you. Yeah? Look at this body now itself. The flow is going from the left to the body, and then behind the body we have this so-called wake region where almost no particles. And what does it mean? No particles for computational of moments of density and so you have no statistics. Yeah, and if you use and really the difference of the densities is about 6. And behind the body, the density is 10 to the power minus 5. It is a multi-scale problem. What can you do? You can increase the whole number of particles by a factor 10 to the power 5. But then you have to buy a new computer for this. And the second thing is to reduce the variance. And if we have 2 particles reaching this region, and suddenly we declare them to be weighted particles. Then in the next collision, they lose the weight, and we have 4 particles. And 18, 20, 100, 300. They're smaller and smaller and smaller, but the number is important. The number of particles is important to reduce variance. And so it is reasonable computation of, we call this rare events. It's possible using weighted scheme. But they are here, that's okay. But they are leaving this region. And they are coming to the region where you don't need so many particles. And then you have troubles. But nothing is for free. If you try to resolve your flow here, you have to pay here. After that, suddenly you have, instead of 1,000 particles, you have maybe 100,000. You don't need so much. And so you have to reduce them to cluster them together again, and to find again small numbers. One of the problems really, the particles can get weight of 10 to the power minus 12 or something like this. And you cannot remove them, otherwise you will get loss of mass, and this is completely not possible in numerical schemes for Boltzmann equations, because it's very natural to conserve the mass. If you once you lost the mass, even in this small amount, everything will disappear. All the realistic results will disappear.
I want to finish with we take a time for 2 more questions, and then we break for lunch. So this question there, second last question, then the last question. Okay.
Okay. Say you use direct stochastic solution. I guess they are not of America. What is unique about direct stochastic solution?
Actually, there's nothing unique here. It's also the equation you use. This direct simulation Monte Carlo is even very classical Monte Carlo scheme for this spatial equation. What is unusual? You can debate. That is not the convergence is deep convergence of complete equations. Yeah, and usual convergence is now this is the following. There are maybe 2 errors. There are 2 errors. One error is the number of particles. it is something like first constant over the number of particles. It converts to 0, 1 over n. And then the second part, it is more trickier. And that is usual Monte Carlo conversion. Start one of the square root of your independent projectors. Yeah. And if you fix the number of particles, if this number is fixed, and you increase only this number, then you have the usual Monte Carlo conversions, stochastic conversions of every stochastic process, one over square root of your independent projector. But in our case, we can increase both of them. And so this usually dominated term in the conversions can be compensated by increasing the number of particles. There's a product of it. For fixed number of particles, there are no chance. The slow one over square root of the repetition. But we have in one parameter more to get better conversions. Okay?
Final question, students, and then we'll break for that. I want to see you with the lunchtime question as well. The lunchtime question is, with all the discussion on bullet boards, how would this inform mathematicians to say something about climate change? So this is the lunchtime conversation. But that last question here. Then beginning with by speaking and okay, this actually it's a wonderful lunchtime.
Okay.
So,
It is cosmology. I tried to do this. I had many conferences in and I know doing research on this, my research was not connected to this. But of course, it can make a huge difference. But the forces taken here, and it is long for this range situation. I mentioned the balances. But Boltzmann equation is the equation of short interaction. Particles do not know about each other. But and it is possible to model by galaxies to model all this in this field. Because there are certain things you cannot say they're all the same. It is somehow one thing. What do you divide? Divide. Quantum mechanics is the game of community and stuff, yeah? Since here, the number of particles in the power. And I mentioned that there is two based on resistance. Here is a very old theory of Euler-Maclaurin. If we have a big sum, how does it produce the number of particles taken out of the and then it was the idea of Euler to write the sum as an integral plus some reminder. And to get this reminder for a regular function, possible take 200 but to get this for singular, even if it's the regular application, it is in the range of convergence representation of the peak sums as an integral which can be computed numerically by quadrature plus remainder which converges against it. So we are at the formula to get a lot of fun. Now we have two functions and three variables. It's just very beginning. And I'm still hoping that he will get Nobel Prize. Not me, but I teach institution. His physics in the past. His study was then he changed for PhD.
Thank you, Professor Reutener. Thank you very much for an extremely delightful and insightful talk. Everyone, just one last round of applause, and then break of hour 45 for a Heritage Day lunch. And then if you could please reconvene here at exactly 1:30, or maybe just a little bit before 1:30. Start exactly at 1:30 again. So just make your way outside, and there's this food, the big food spread, etc. Interesting.
Yeah, okay, thank you.
Thank you very much. For the
We will try now the equipment.
Yeah. So it has the USB-C.
Yeah, everything is available here.
We also have HDMI. USB-C, I think, is the one that works best for my track for lunch.
I go if they want to come for lunch as well.
Okay, well, good. I think. I mean,
They were still asleep when I left.
Ulrich, my wife is with me. Is it possible that she will attend the lunch as well?
I'm bringing my family as well.
Yeah?
Yeah, because they also want to meet you.
She's in Bath. Maybe you can invite her.
Oh.
Some years ago, so I have came to 100 questions in each. It's really difficult. I'm not a software company. But personally, I think
Support for an expert, but it's super impressive, really. That is so. It's like this kind of boundary where you have more.
this is artificial thought. And on the left wall, this is inflow thought. I assume the shuttle is moving from the free state. And suddenly it picks up.
Yes, so there is actually this
Yeah.
boundary.
So the particles are coming, or the single flow, because the movement is relative. Yeah?
Yes.
In reality, of course, it is more and slowly dance and dance and dance. But in the simulation, we neglect the first phase of the simulation. Steady state is better.
Okay, so in real life, this boundary would be more of a gradient, right?
And the other boundaries, there is outbound. In the particular each application to maybe it will disappear simply.
Okay, we expect. This recipe is really interesting.
Thank you. What? Hat doch dir gesagt, dass du eingeladen bist? Sei mit uns. Deine Frau. it was in Germany. This was some collaboration between the East Germany, and this time it was not really in Cameroon. So we have got students in Saxony.